Morning, everyone. Can you hear me in the back? Okay. All right, let's get started. Today we're going to be talking about another one of our computational patterns called parallel scan. This one seems a little obscure. Probably nothing you've encountered maybe while you're coding. But it's an important one, and we'll get to it. It's very easy, like once we describe it. But the computational pattern in terms of parallelization is a little involved. So we're going to spread this one across 2 lectures. Today we'll talk about a version that's good, but it's got some properties that maybe we won't like so much. And then we're going to refine it on Thursday with an improved version. Okay, parallel scan. A couple of things. Last time when we met, I mentioned a course I'm planning on teaching next semester. And at this point, I'm committed to doing it. So if there's a few of you that were interested in taking it, turn down the microphone. I think that's the microphone. Okay, can you still hear me in the back? Yeah? Okay. So the course is let's call it a design course on accelerator architectures. And as this is a programming course on accelerator architectures, that'll be a much more hardware-oriented course. For students who've got a background and an interest in things like ECE 411. So if you're taking 411, you're ready to take the course. I got some good feedback from several of you who spoke to me afterwards, and then also sent me an email. I do think the course will be a 4-credit-hour course. Does that work? Like if I propose it as a 4-credit-hour course, would that fit in schedules? Comments? Anyone? Yeah? Okay. What that means is there's going to be some work involved. And hopefully that doesn't scare you away. So by the end of this week, I should have a pretty clear syllabus and workload requirement document in hand. And I'm willing to share that with anybody who would like to see it. Okay. Okay, so that was the first thing. Any questions on that? Okay. Next, just a bunch of reminders. Project Milestone 2 was released last week. It's due on November 4th. So we've got some time to get it done. It's the baseline convolution kernel. So it'll be a CUDA version of Milestone 1. Okay. Not yet optimized, because what we're going to do for Milestone 3 is to really start to dig in and improve the performance, the throughput for the inference pass through the convolutional neural network. Again, by accelerating the convolutional step. And it's on this one that we're going to be providing some extra credit opportunity. Okay, several of you have asked me, will there be extra credit? And the answer is yes. And it's going to be based on you doing extra optimization up and beyond what's kind of the basic requirement for Milestone. Okay, details will come when we release Milestone. Okay, Lab 5, reduction part of Lab 5, 5.1 is due this week. The scan portion of Lab 5, 5.2 is due next week. So reduction is what we talked about last time. Scan is what we're going to talk about this time and on Thursday. And you'll just kind of go through and implement this. Okay. Any questions on that 5. Pretty straightforward. And then finally, midterm 1. The average was a 64. And it's probably a little higher than I expected, so that's good. And the standard deviation was 17.4, which is also very good. It gives us a nice spread. I don't anticipate a lot of regrade requests because most of it was done auto-graded because of the multiple choice. And the coding questions, I think we had a very strong rubric that we followed. But nonetheless, if there are things that you want regraded, please submit them by Friday at noon by sending me or Professor Kindertinko or Gwenan Gu an email. Okay, I posted something on Campus Wire about that yesterday. Okay, good. Any questions? Yes?
Could you quickly go over what milestone 3 and
Milestone 3. Yeah, so what we're going to do for milestone 3 is give you a list of optimizations that you can try. Some of them will work and some of them may not work, but the idea here is, okay, it's a big, hefty kernel with a lot of input data. Go and optimize the runtime. You know, you'll apply things like memory coalescing, kind of retiling the algorithm. You kind of do a search for the right block size and the tile size and this and that. Okay, those are the simple things. But then there's some more algorithmic things you can do, like, you know, converting the convolution into a matrix multiply, which might help, which might not help. Kind of depends. So there's a list of things you can do. And you'll implement, I think it's like 3 optimizations out of that list. Okay, that's the idea. Does that make sense? Yeah. Question.
So in terms of we're going to do a list of optimizations we can try, if we jump to performance permute between different combinations.
Yeah. So not everything will be beneficial, right? In real life, you know, you don't always know what the answer is. You got to go and discover it. And we're not penalizing you for that. Like if you implement something and it doesn't work out, that's fine. Just show us why it didn't work out, right? So you'll be doing things like running insight tools, and you'll look at, you know, the compute, and you'll look at the bandwidth, and you'll say, well, I thought this would work, but really I was limited by this other portion, for example. Okay. So it's the report that lets you kind of justify what you did and analyze what you did. Okay. Good? So yeah, that's anything else? Okay, great. Let's talk about scan. So let's first start off with a definition. Okay, and then we'll kind of motivate why this is something we even care about. So let's say we've got a binary associative operator, abstractly, that symbol there, and an array of elements, x0 through xn minus 1, so n elements. What we're going to do is we're going to define scan. Sometimes we call it the prefix sum. It's kind of a more historic name for it. As essentially, if I have n inputs, I'm going to have an n element output. So it's not a reduction. I'm going to have n output elements where the first output element is just x0. Second output element is x0, x1, x0, x1, x2, and dot, 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 such that the last element is all the elements with the operator applied. And that's actually the reduction that we spoke about last time. So for example, if the operator is addition, then the scan operation on this input array, 317041163, returns this. So 3 3 plus 1, 3 plus 1 plus 7, and so on and so forth. Okay? Kind of a strange operator. But it turns out it's one of those things where you're trying to parallelize a complex piece of code, and hey, boy, I really need to calculate this because that's what I need to do to unlock the parallelism. So you probably haven't encountered it frequently unless you've done a lot of parallel coding in your past. Okay, so it's one of those things that you need it, and you need to often calculate it in parallel because of reasons I'll explain. So that's what we're going to talk about. We've got this operator here, and we want to calculate it in parallel, efficiently. So how are we going to do that? But before we do that, let's talk about kind of some motivating examples. Okay, let's say we've got a piece of wood, 100 centimeter piece of wood. And what I want is, I need some pieces because I'm trying to build something. And I need a 3 centimeter piece, I need a 5 centimeter piece, 2 centimeter piece, and so on and so forth. Okay, so I could, for example, apply it like you and I would apply it, which is, okay, first, I cut a 3 centimeter piece, and then a 2 centimeter piece, and then a 5 centimeter piece, and then so on and so forth. Right? The sequential version is, well, trivial. Kind of the natural, innate way we'd apply, kind of approach it. But if we had in fact, the saws that we create, right, you can imagine a thing that cuts wood. It's really cutting one piece at a time. But if we wanted to create like the GPU version of a saw with lots of blades, which you can imagine like if we're designing a high throughput manufacturing line, yeah, we're going to do things in parallel. Okay, now I need the prefix sum. I need the scan version of this, right? Because I need to know where to make the cuts. The first cut is at 3. The second cut is at 8 centimeters, right? Because I need a 5 centimeter piece out of that 3, after the 3 centimeter piece, and so on and so forth, right? So converting that sequential process into one that's higher throughput requires the calculation of the prefix sum or scan. And these kinds of examples, again, in the parallel programming world, just kind of appear as we're trying to do things. Okay? Make sense? Yeah, I think when I encountered this thing, again, as an undergraduate student, I was like, I don't know when I would ever apply this. But again, it pops up as we're trying to map things into parallel. Yeah, question?
This reminds me of
Yes. Yeah, I mean, essentially this is kind of like an integration of the input values, right? Just like a CDF is an integration of a PDF. Okay, so yeah, very much related. Okay. So the sequential version, yeah, that's pretty easy, right? I just go from 0 or 1 to n. I don't need to calculate the 0th element because, well, it's just the identity. And the output is essentially kind of a recurrence, really, right? I'm going to take output of j minus 1, add to it f of j, which is the input, in order to calculate the jth output. Now, in parallel, assuming we had a parallel scan, I would just copy the input to the output and then apply the parallel scan. I guess we're going to talk about that parallel scan for the rest of the lecture, in fact, even on Thursday. So again, I keep emphasizing, well, yeah, it sounds weird, looks weird, never thought to calculate this before. But you can imagine, well, let me just say that as we talk about parallelized versions of things like quicksort, string comparison, this thing pops up. Maybe one that you can relate to. On a network, a high-speed network interface controller, we've got lots of incoming packets of various sizes. Sometimes those packets are coming in so fast, they get buffered up. And then maybe they're coming in parallel because I've got multiple input ports. Now, in order for me to do buffer allocation, I've got a packet of size 3, packet of size 5, packet of size 11, packet of size 16. These are all coming in. Well, if I want to do buffer allocation in memory, I have to essentially do something like a prefix scan, prefix sum or scan, in order to do that buffer allocation, right? So you can see how this thing tends to pop up. Good? Any questions? It's a very basic, simple thing. Okay. So the sequential version, of course, you all get it, right? It's very easy. You can even write up a recursive definition, just like I showed you before in the sequential code. Okay. How would we do a parallel version of this? Again, for reference, here's the sequential version. How would we do a parallel version of this? Well, you might think, okay, easy, no problem. I've got a bunch of threads. I'll have n threads. I've got n input values. Thread 0 calculates y0. Thread 1 calculates y1. Thread 2 calculates y2. And so on and so forth. Done. Submit 5.2. Why is that bad? Why would I not consider that to be a real solution? Okay, several of you are seeing it, but I'd like everybody to be there. Yeah, why?
You did your sheet. Copies of the input.
Okay, yeah, there could be a memory issue, but even before the memory issue is something that we need to talk about. Every thread is adding a different number of elements. Maybe that's okay. Again, memory issue, imbalance, you're talking about an imbalance, but something even more fundamental. Yeah.
The last thread is doing an open.
Yeah, that last thread, thread n, is essentially doing the same work as the sequential thread. It's no different. Right? So we created all this parallel work, but it's still an order n algorithm, even with an infinite number of parallel resources. Right? Even if I had enough memory bandwidth, even if I had an infinite number of parallel resources. Which brings me to one of my favorite sayings in parallel programming. It's easy, as long as you don't care about performance. I mean, parallel programming, by the way, let's not confuse it, is nothing magic. Parallel programming is optimization. That's all it is, right? It is, I've got this piece of code, I have a sequential version of it, it works, but I need it to run faster. That's all it is. So, yeah, we can take that code and we can build it as such, but it's not quite there. Now, some of you are thinking, hey, look, we just had this lecture last time on parallel reduction, right? What is that nth thread doing? It's doing a reduction across all n elements, right? So maybe your mind is already thinking, well, couldn't I, at least on that last thread, run it in log time? Yeah, you could. But what about n-1? Yeah, maybe I can run that in log time too. Remember, I need lots of resources to run it in log time. Right? How many resources do I need? Threads do I need? And over 2. Right? So something is like, well, it's not, hopefully in your mind you're like, yeah, I can do it, but I really need a lot of resources. Right? So, okay, this is kind of funky, right? It's not like trivially something we can approach and just spawn out a parallel version of this. Everybody following? Any questions? Okay, cool. So what we're going to do is we're going to come back to kind of basic principles. Okay. And the idea here is if you sat down and you looked at the pattern of a scan, what you'd notice is there's a lot of redundancy in the computation. Okay. And what we can do is kind of reorder the computation a bit in order to get that logarithmic behavior, first of all, right? Because if the sequential version is order n, we want to do better than order n if we can. And to reduce all the computational needs, right? Where we had n over 2 threads just to calculate the last output value. So we're going to get inspired. In fact, I like this design a bit because it's inspired by hardware. Okay, back in the 1970s, when things like doing multiplication in hardware was the stuff of PhDs. Okay, where the circuits were large, right, and they cost, you'd have to put a whole chip just to do one piece of a multiplier. Multiplier was multiple chips and probably maybe even a board in a very large computer. People thought heavily about, well, how do we reduce the number of gates in a multiplication tree? Okay, so Peter Kogge and Harold Stone at IBM had created this multiplier design, right, to add 2 binary numbers, A and B, multiply them together. Pause for a moment. How do you multiply 2 binary numbers together? Yeah? You could, right? You got the, you get a B, right? You got the correct version, which is good, right? You didn't get a C. That's, kudos to you. But how do we do better?
That's
A cool shift-add method, all right, B+. The reason why repeated additions and shift-add maybe aren't the best is because they're iterative, right? We want to do something that's not going to take multiple steps, right? Can we do it in a single step? How do we multiply by hand? Like if I give you an n-digit number and another n-digit number, how do we multiply them? We don't shift-add. We don't, thankfully, do repeated additions, right? But how do we do that? Yeah?
You multiply all digits of A by...
Thank you. Yeah, perfect. Right. I like the way you've described it. So I have all the digits of B, I have all the digits of A, and really what I'm doing is an array. Okay, it's like I've got this 2-dimensional table I'm going to generate of all the partial products. That's the name we use for these. Okay, that is a tree, ultimately. So we're going to get, they were inspired by that tree. A multiplication tree, multiplier tree. So each multiplier tree is doing a single-digit multiplication, which in binary, it's either you're multiplying by 0, which is 0, thankfully, or you're multiplying by 1, which is a number, right? That's where the shift-add, by the way, comes from. Okay, so the multiplication by 1 bit, thankfully, is super easy. And really what I'm doing is I'm kind of tabulating everything and then doing what? A big addition at the end. that is essentially the Kogge stone tree with some, kind of reductions and removal of gates along the way. Okay, so you've got that in your mind. Okay. And now what we're going to do is we're going to take that concept and we're going to apply it to this thing we were just talking about, the scan. Question.
Just to clarify, is what we're doing here, just like taking the number and having different like left-shifted versions of it?
Hang on. Are you talking about multiplication or are you talking?
Multiplication. Is the thing that you're
Yes.
doing all the
Yes.
adds in parallel?
Yes. 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 So when you say shift add, okay, shift add is just a unrolled, or let's say, is a way of stating the unrolled version. Okay, the multiplier tree is the unrolled version of the thing you just described. Make sense? Okay. Okay, good. All right, so let's get into it. So let's start at the very beginning. Okay. And what we're going to do is we're going to assume we've got some input, T. 317041163. We can make it simple. It's a power of 2. So we always have a power of 2 set of input elements. Okay, T. There it is. And I'm going to use this iterator called stride. Okay, and stride is going to go over, we're going to multiply stride by 2 each time. We're going to go to n over 2. And I'll tell you more as we go through this. Okay. So already, because I'm going to n over 2, multiplying each time, multiplying by 2 each time, it's going to be a logarithmic number of steps. Okay. So in that first iteration, I have essentially 8 threads, actually 8 minus 1 threads active, 8 minus stride threads active, to be completely accurate. So 7 in this case. We could have 8 threads. That first thread could just copy the 0th element to the output because 3 is 3. The 0th element just passes through. Okay. Now thread 1, in this case, and I'm just going to write this on the slide. Thread 1 here, right, that's thread 1. Thread 1 is adding 3 to 1 to generate the 4. Thread 2, thread 3, 4, 5, and so on. Right, so in this case, all the active threads are just adding their, let's call it their home element, which is this element right here. Each one takes its home element, and the one just to this side, I guess the left side, if we're facing the screen, adds them together. And then we have, this is the output. Okay? Now, in the next iteration, we're going to multiply stride by 2. So it's going to be 2 in this case. And we're going to deactivate stride threads. So we're going to deactivate these 2 threads. So really we have threads 2 through 6 in this case, or 2 through 7 in this case, that are active. So now each thread in this case is going to take its home element. So in the case of, so this is thread 0, thread 1, thread 2, 3. So in the case of thread 2, what we will do is we will have thread 2 take the 8, add it to the 3 to generate the 11. Okay, So let me say it again. Instead of going one element over, we're going to go 2 elements over and add it to the home element. 2 being the stride. And you're going to see on the next slide when stride is 4, we're going to multiply stride by 2. We're going to go 4 elements over. Okay. So here we go. The next iteration, stride 4. So at this point, the first 4 threads are inactive. Again, we're reducing the number of threads by stride. And then the active threads, which in this case, thread 4, 5, 6, and 7, are going to be adding their home elements to an element that is stride over to the left. That's the same pattern over and over. Okay. Seems like magic, but yes, it works. Right? Because at this point, what we have in the output after this 3rd iteration is the scan. Okay? Any questions about the pattern? We're going to come back to it a couple of times just to make sure we're all on the same page. Actually, there's a bunch of pitfalls in this. We're going to get to those as well. Any questions, though, on the basic idea? So, yeah, maybe you can map this into multipliers. It's not totally obvious to me, but this is essentially the same as the Kogge stone multiplier design from the 1970s. Okay, any questions? All right, great. Let's take this and start to dissect it. So what we want to do right over the next few slides is kind of take that sketch of a data flow, computational data flow, and start to arrive at some CUDA code to do this, the kernel code that accomplishes this. Okay, so step 1 is easy. We got to get the stuff we want to scan into memory, or into shared memory. Okay. By the way, just as an aside, we'll get to this later, but if I have a huge number of elements that I want to scan, I can break it up into smaller scans. It's not totally obvious, but we will. Okay. How we do that. So, for now, let's concentrate on one thread block. So what that thread block is doing is it's going to take some elements from global memory and copy them into shared memory to start with. Okay, that's what step 1 here is. And we're going to assume that this block is a power of 2. So we're going to copy power of 2 elements into shared memory instead. Okay? Now, we kind of want to go and start to describe the computation. And I think I did that as we were walking through the computation flow. Okay, so the number of active threads we're going to have is essentially starts at stride. So we had stride starting at 1, then we multiplied it by 2, then we multiplied it by 2, multiplied it by 2. So 1, 2, 4, 8, so on and so forth. So the number of active threads are really stride to n minus 1. And the way to think about that is as I'm going through the tree, I'm calculating T0, T0, T1, T0, T1, T2, T3, dot, 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 dot. They're all done, right? And then what each active thread will do, so active thread J will add elements T sub J, which is what I've been calling the home element, and then T6J minus stride. Right? That is reaching over stride elements to the left. And then I write the result into T6J. Then I got some sync threads I got to deal with, but I'm going to get to this in a second. Okay. Any questions on this sketch right here? Right. What I haven't proved to you is that this actually calculates a scan, but we'll leave that for later. Any questions? Okay, cool. Well, here's where it gets a little tricky. Let's talk about the sync threads. Okay. I need a sync threads at the top of the loop. Why? What does this sync threads accomplish right here? See a couple of hands. I want to have everybody think about it, and let's try to get to the same point. Yeah? Go ahead. Right, perfect. Very well said. I'll restate what he said, which is this first sync threads synchronizes that the inputs are available. Whether the inputs are coming in from global memory into shared memory, or that the additions from the previous step are all done and the outputs have been written. Right? Basic, got to do that. Yeah, question?
Wasn't loaded from global. So in the shared memory, I need to stay. But wouldn't a previous iteration
Hang on. Let's get there. Okay, let's hang on. Let's get there. Okay, so now, with that said, we have this other sync threads. Okay, why is this sync threads necessary? And this is a very subtle reason. There's a very subtle thing here that is not completely obvious when you first look at it. It's also false. We'll get rid of that in a moment. Yeah, but go ahead.
Since modifying the array in place, we could end up with a new T of J value.
Beautiful. Okay, what he's saying is, okay, if I write this T of J, right, let me go back to the previous code. Actually. So if I didn't have the sync threads, let's assume that's not there for the moment. Okay. So, and I just put this T of J right here and I get rid of this temp thing. What's happening is I'm reading T of J and I'm writing T of J. Okay. Other threads might be reading T of J as well. In fact, they do, right? If I look at the top here, I've got, let's see. Let me take, for example, here. Let's say this is T of 5. Right, so this thread 5, happens to be writing T of 5. But there's another thread that's reading T of 5. What is that thread? So thread 5 is writing T of 5. But there's another thread that's reading T of 5 in the same iteration. Yeah? Thread 6 is reading it, right? Thread 6. So we've got T5, T6. Thread 6 is also reading this value. It's trying to read the 1. Okay? So T of 5 contains 1 at the start of the iteration. It contains a 5 at the end of the iteration. Thread 6 is trying to read the 1. Thread 5 is trying to write a 5. If thread 5 beats thread 6, we end up with the wrong value being read by thread 6. Question? Exactly, yes, yeah. Yes. So if we got a warp boundary, which it makes it even worse, right? You could write this code, it could work most of the time. And then on some strange iteration where you got the warp boundary crossed, it doesn't work, right? It makes it even more onerous to debug. Yep.
This just that error case in terms of when it's not the warp boundary, isn't it basically in this case we have like 2 second threads? Isn't it sort of like almost FPGA metastability state, like who wrote first exactly, who knows who end?
I'm not sure I understand your question.
It's always guaranteed that this will work if you're not on a warp boundary.
Is it guaranteed to work if you're not on a warp boundary? Yeah, because in a warp, all the threads are executing the same instruction, right? So you will know that thread 6 is reading the input at the same time thread 5 is reading input. Thread 6 is writing the result at the same time thread 5 is writing the result. Okay, so never an issue there. Make sense? Any questions on this second sync threads? Yes?
Is there any reason to do this instead of creating?
You got it. Hang on. We'll get right there. Okay. By the way, sync threads are bad, right? They're necessary. We need to put them there in order for us to get the thing to work correctly. But they're bad for what reason? Why would I not want sync threads other than correctness? Yeah?
You're imposing some degree of serializability.
Yeah, we're putting a serialization constraint on the code, okay, which breaks down parallelism, right? It's also expensive to execute on a GPU. Those instructions take time. Remember, a sync threads is essentially a loop. Right? Wait here until all threads in the block have reached this point. So lots of threads are just waiting, doing nothing. Okay. So we don't want to introduce sync threads unless we really have to. Make sense? Yeah, question.
I think after this I can answer the question. For sync threads, so that you can make sure like when the thing loops, all the TJs write at the same time, right?
Exactly. Yes, exactly. Yeah, we need to make sure the TJs are done because we'll never be sure of that because some warps can be arbitrarily delayed. Right. Okay. So, by the way, this one here is dealing with something in the architecture world we call a false dependence. Okay. It's not a real dependence. This is a real dependence here. The sync thread is due to a real dependence. I need this or this, this and this to be ready and available before I do the addition. There's no way around that. This one is not quite the same. here, thread 6 was trying to read TJ. Actually, it was trying to read this one here, this operand. At the same time, thread 5 was trying to write into that same memory location. This is what we call an output dependence, as opposed to an input dependence. It's not a real dependence, and it only occurred because we're reusing memory locations. Right? Just for the compactness of this algorithm, I'm reusing T sub j for thread 5. So it's not a real dependence, and we're going to break that in a moment, okay? But before we do, let's just appreciate for the moment how this particular Kogge stone multiplier tree works, okay? And it works because what we're doing is we're sharing computation across the output elements, okay? We can take a look at how we end up generating this 25. So we've got this thread 7, that's doing a bunch of adds. And when it's doing these adds, what it's doing is essentially picking values that were computed by previous threads. Such as thread 2 and thread 4 in order to calculate that 25. So we kind of follow the flow of computation for thread 7. And let me just... So thread 7 calculates essentially from this tree right here some part of partial sum. And then we're using values that were calculated here again by threads 2 and thread 4. Some more by thread 4 in order to calculate the final value. So it's that tree, it's like a bunch of embedded trees that we have for calculating this element, and this element, and this element, and this element that help us do this in logarithmic time. Okay. Essentially, when we were talking about that problem at the beginning, where I said, well, that nth element is a reduction, it's just that we've overlaid that reduction in a nice way to make it all compact. Okay. Kind of a hand-wavy way of describing how this thing works. We put it all together, and here it is. Right? Here's a partial implementation of the Kogge stone scan kernel. And what I'm saying here is I remove that sync threads, that second sync threads. So there's a data race here. That you did this, it might work most of the time. Occasionally it'll fail. And it's because of that sync threads that you need at the warp boundary. Okay. So what I want to talk about next, by the way, before we go on, any questions about this? Just kind of walking through it, right? We start at stride equal 1. We multiply stride by 2 all the way through. And we stop when stride is bigger than block dimension x. Really, that's a way of getting to n over 2, or block dimension x over 2, right? Because we multiply it each time by 2. And then all I'm doing is I'm incrementing thread index x with thread index x minus stride. Okay, so that said, I want to introduce a concept to you that, if I have to pick the top 10 things that as a ECE undergraduate, or maybe even computer science undergraduate, that you should take with you and treat as a design idiom for everything you do forward. This is one of them, one of the top 10. I've done a lot of system design in my life. This is just there all the time. The idea is really simple. It's called double buffering. And it's a way we're going to get past this second sync threads that's in our code. Okay. You should know this, right? It's one of those idioms you will use over and over if you're, going to put your degree into practice. The idea is very simple. Sometimes we call it ping pong buffer. Okay, but the idea is here. It's essentially this. Instead of having just one T, right? T was where we put the global memory, the shared memory, the variable T. We're going to have two T's, T0 and T1. Okay. And what we're going to do is, iteration 0 will use T1 as input. T0 is input, and T1 is output. Iteration 1 will switch T1 as input, T0 as output, and so on and so forth. Okay, so the idea here is that instead of one buffer in shared memory, we have two buffers, double buffer. And by introducing that extra memory, what we're going to do is get rid of that output dependence, that false dependence that we introduced into our code because we're reusing memory. And it turns out to do this is trivial because we can use pointers and we can just swap pointers and there's no copying back and forth that we need to do. And if we do it right, the cost of this is almost zero. We get rid of that second sync threads, which is huge. Yeah, question. Okay, there's the cost, right? Because in order for us to do this, we have to essentially double the amount of shared memory we need. Right? So one of the things about GPU programming and like optimization in general, code optimization, is sometimes that cost matters and sometimes that cost doesn't matter. And it's just got to go and try it, right? Does it work? Does it not work? In fact, milestone 3 for the project, I expect you all doing that, right? I have an idea for improving the code. I'm going to go try it. I'm going to have to experiment because it's never going to be clear as to whether or not it works, right? That's your point, right? Yeah, I got to double the amount of shared memory I need. What's the cost of doubling the shared memory? What happens as a consequence of that? Yeah? Probably the number of blocks I can put on an essay goes down, right? Which may have negative consequences. Make sense? Okay, but let's say we wanted to try this. So what does the code look like for that? Well, what I'm going to do is I'm going to create source, which is the address of T0, and destination, which is the address of T1. Right, in C++, I've got the address operator, and I can take the address of buffers. So instead of using T, I'm going to use source and destination. Okay. And then what I'm going to do is swap them. So here, I just have some code to swap the two, and I go back through the loop. That's it. Okay. The idea is so powerful that we see it all the time when we're doing this kind of memory, kind of low-level system design, double buffering. Yeah.
Why would you swap instead of just clearing them? You don't have to have, like, let's say I have two memory addresses that I'm writing to and I'm XORing or like double buffering between them. So let's say my current input is T0 and my output is T1. When I want to make T1 my input, I just need to like copy the T0 plus Tj at 0 and Tj minus 1, right? I need that. But I don't need to essentially have T1 copied over here, right? Or you do because you're adding still?
Yeah, I need to. I mean, all I'm doing here is swapping the pointers. I'm not copying anything here.
Oh, okay. So you just reference to
The references, right? So all I'm doing is I'm swapping. Okay, I've got this variable source and I've got this variable destination. Source points to T0. Okay, so I've got source and destination. These are just two variables in my code. They're pointer variables. And I've got T0, big array in memory. T1, big array in memory. Initially, I set source here and destination here. So they're pointing there and there. Now, when I execute this code here, this line, all I'm really doing, is I'm just taking those values and swapping them. Okay, so it's just reassignment of those pointer variables. It's very efficient to do that. Okay, make sense? Any questions on this? So this is essentially what you will be doing for 5.2. Okay, yeah, question? There's no copies involved. Yeah, we're still writing either to T0 or T1, right? Depends on which one is which. So we're still writing, but then we flip from where we're reading and from when we're writing. Okay. Okay, good. All right. Let's move on. And kind of what I want to do is end here. So, sort of a strange thing with this algorithm. Okay, so if we analyze how many steps we need to do this, it clearly takes log n steps, because we're going to do, in that first iteration, we're going to have n minus 1 steps, additions, then n minus 2 additions, n minus 4, all the way to n minus n over 2. Okay. So the good news is that's logarithmic, because that's the total number of steps in my tree. But if I sum up all the operations I need to do, that is, how many additions do I do in this, there's a bit of bad news here. Okay, and that is that if I sum all this up, if I take the sum of n minus 1 plus n minus 2 plus n minus 4, I end up with order n log n work. How much work was in the serial version? Not log n, order n. Right? So the serial version had order n work, order n steps. this one has log n time, but n log n additions. So the work efficiency of this algorithm is not very good. Right? What it means is, let's say, for example, I've got 1,000 elements. Or I'm sorry, 1,000,000 elements I need to add. Okay. I have 20x the amount of work I need to do in the parallel version as opposed to the serial version. Okay, so I need a lot more resources in order to accomplish this in a way that's advantageous to me. Okay. So if I'm resource constrained, like if I don't have enough threads, then we may not outperform the serial version just because of the work efficiency of this algorithm. What we're going to talk about next time is a more work efficient version of this that is better than this one. And in some sense, can outperform this one. And we'll talk about it next time. But before we wrap up, any questions on this?
When you say sometimes the parallel version is not as good, is that just because the number of threads might?
Yeah, I need 20 times the number of things, right?
Or is it also considering
There may be memory bandwidth overhead. There may be additional overheads. Maybe I need more shared memory because I need lots more threads. There's a lot of things to consider, and it's going to be the fact that even when I introduce the next version of this, which is the Brent-Kung approach, it has better work efficiency. Okay, but it may take longer. So we got to balance all of these things out. Yes.
When the block is done, it only calculates the.
Great question. So what if I had a bunch of elements, 1,000,000 elements? Each thread block was calculating, let's say, 1,024 elements. So I've got a bunch of scans. Right? So I do blockwise a bunch of block scans. Now, how do I aggregate them? We'll talk about it next time, but let's think it through. Do it again? What do you mean? Almost. Right? I don't want to recalculate the scan of a block. But kind of, if you think about it, if I have block 0 and block 1, let's only take 2 blocks. So I take those 2 blocks and I scan them. And I have output. What I want to do is I want to take the last element of this one and add it to this guy, right? Because this guy is correct, except he's a little offset. Right? He's offset by whatever the scan was of this one. Okay. What about the third block? What about the fourth one? Well, really what I want to do is a prefix scan of the intermediate results. Okay. We'll talk about this next time. Kind of do it carefully for everybody. Okay. But you can do this hierarchically and actually have it work quite efficiently. Yes.
So the current method should only ever come when the per thread block have divergence, because it'll have like the first thread do nothing, and then the first 2 threads do nothing, and then so on.
Exactly. Yeah. Exactly. Yes. Okay, great. So that's it for today. When we meet next time, we'll do one more pass-through scan, and then we're going to talk about histogramming after that. Okay, thank you.
Testing, 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 testing.